For section 8.5, we look at partial fractions. So first off, we have to kind of look at what is a partial fraction. So given if we have a function that's made up of two sort of rational function pieces that are either added or subtracted together, right? When we want to combine those into a single fraction, we have to find a common denominator, and so that usually involves multiplying the first fraction in the numerator and the denominator by the denominator of the second fraction, and likewise multiplying the second fraction, numerator and denominator, by the denominator of the first fraction. And so we would combine the fractions together, add the numerators together, and so we would get some sort of single term in this particular case, numerator, and our denominator, we would have these two factors multiplied together. We expand here. And so what we want to do in partial fractions, as it says here, is reverse that process. And so when we add these numerators together, you kind of see that we lose some information. There's all kinds of different terms that we could end up adding or subtracting to get 3x. So which one in particular would we be able to split apart to be able to get these original fractions? So there is going to be a nice way to find that and a nice algorithm that we can use. So what we're going to do is, given something like this in an integral, it would be pretty difficult to integrate. But if we break it up into these two smaller pieces, these are going to end up being much easier to integrate. So what we'll do is we'll set as our goal here to start with this on the left side here, this difficult to integrate, and then we'll end up with the right side that's easier. So we want to be able to take a fraction that looks like this, be able to factor it, and write the fraction as a constant over the first factor plus a constant over the second. So we've got a and b as our constants. And so this process of splitting these guys apart is going to be partial fractions. And this expression here that we get with the a and the b is going to be our partial fraction decomposition, or PFD. In this particular case, it's got two terms, one for each factor. And so that's going to happen pretty consistently here. So what we'll have to do is use some sort of algebraic manipulation to figure out what a and b are. The idea is the original function and its partial fraction decomposition must be equal for all values of x. So we'll go ahead and look at a way that we can go from this first fraction to its partial fraction decomposition. So we'll go ahead and start out with this original fraction here. And what we'll want to do is the first kind of step that we'll always take is we'll have to factor out the denominator completely. And so this is a trinomial. We'll be able to factor it into two binomials. And we look at what are the two numbers that multiply to give us -8 but add to give us 2. And so that'll give us +4 in one factor and -2 in the other. Right? And this does match up with what we had originally here. And so we know, again, that this should be equal to a constant over x minus 2 plus a constant over x plus 4. Right? And the reason that we know this to be true is because the denominator is degree 1. And we know that we're supposed to end up with a proper fraction. The degree of the numerator is lower than the denominator. So if the denominator is degree 1, then the numerator must be degree 0, which would be a constant. And so what we're going to do from this point is we want to get rid of our denominators. So we'll go ahead and we have both sides of this equation here. We'll go ahead and multiply them by both denominators. And so we'll multiply the right side as well. And on the left side, both denominators should cancel. And so we just get 3x. On the right side, we'll go ahead and take each of these factors and distribute. And so we'll have some cancellation happening here. In the first fraction, the x minus 2's will cancel. We'll get a times x plus 4. And in the second, our x plus 4's will cancel. We'll get b times x minus 2. And so the first method that we'll go ahead and use here will just be comparing the powers of x. And so what we'll want to do is we'll want to expand the right side. So we'll go ahead and take our a multiply it in, we get ax plus 4a. And we'll do the same for b. Multiply b in, we get bx minus 2b. And so the next thing we'll want to do is we'll actually take the different powers of x and group them together on the right side. So we have the first power of x here, we have ax plus bx. And then we have two constants, so plus 4a minus 2b. And so what we'll do at this point is we'll go ahead and factor out an x wherever possible. If we had an x squared, we would factor out an x squared. Right, we'll just go through and factor out whatever the highest power of x we can from kind of each group. And so we'll go ahead and look at the left side versus the right side. And so like it says in this sort of block of text here, right, the constants a and b are determined using the condition that the original function and its partial fraction decomposition must be equal for all values of x, which means that the coefficients must actually be the same. That means that a plus b must be equal to 3, and 4a minus 2b would be equal to, the constant on the left side here is actually 0. And so what that gives us then is a system of two equations with two unknowns. And so we'll have to go ahead and solve either using substitution or elimination. So the way that I'm probably going to handle this is using elimination here. So we have a plus b equals 3, 4a minus 2b equals 0. I'll go ahead and multiply this top equation by 2. So that 3 will become a 6 instead. And we'll add these up. 6a equals 6. Divide both sides by 6, a equals 1. And so we take that, we plug that back in here. 1 plus b equals 3, so b equals 2. And so those are the two constants we need. So our partial fraction decomposition for x squared, let's see, plus 2x minus 8 is equal to, we have a is 1 over x minus 2, plus b is 2 over x plus 4. And so that'll be our partial fraction decomposition there on the right side. So that is going to be one method for finding out what these constants should be equal to. And so we'll kind of generalize here. It says the previous example illustrates the case of simple linear factors. So the denominator of the original function consists of only linear factors of the form x minus r. So in this case, we had x minus 2 and x minus negative 4. So the thing that they have in common there is we have a coefficient of 1 in front of the x, power of 1 on the x, and then just a constant. So whenever we see something like that, here's going to be our procedure. So first off, we'll suppose that f of x is going to be a polynomial over a polynomial, right? And we're going to have that q as the product of simple linear factors, right? So we start with that. So we'll factor the denominator, and so everything is just going to be x minus a number. Right, those will be all of our factors. Then we'll go ahead and make our partial fraction decomposition. And so we'll have that each of these factors is going to be in its own fraction with a constant over top of it. And in general, if we have a huge number of factors, right, we'll use a with some subscripts. As it was in the last example here, and in many of the examples that we'll look at, we'll go ahead and use capital A, capital E, capital C, just so that we don't have to use subscripts. Right, so the next thing we do after we write it in this form is we clear the denominators by multiplying this guy here by the product of all of the denominators, or it's the same thing as q of x. Right, and so that should cancel out q of x on the left side, and it'll cancel out each of the denominators on the right side and leave kind of the rest of the denominators multiplied by each of our a's. Then we'll solve for our coefficients. And as we get higher powers of x, we're going to end up with more complicated sort of right sides. In this case, we just had a first power and constants. We'll have to kind of group our powers of x together and factor the x's out. And we'll go ahead and take a look at even a simpler method coming up here in just a sec. Right, so like a fraction, a rational function, as we say, is in reduced form if the numerator and denominator have no common factors. So reduced form is good. It means that things are kind of simpler for us. Furthermore, it's said to be proper if the degree of the numerator is less than the degree of the denominator. So that is something important that we want up here. We want to have no common factors, and we want to have the degree of the top less than the degree of the bottom. If one or more of those things are not true, we need to fix that. If we have common factors, we want to cancel. If our fraction is improper, we're actually going to have to do some long division. All right, so we'll go ahead and look at this next case here, and we can do a quick check first of all to see if it's proper. We have a second power in the numerator, third in the denominator, so we know this is proper. We will have to see if there are any common factors to cancel, but since our first step is to factor, we'll go ahead and do that at the same time. So we want to find the partial fraction decomposition, and then we're actually going to integrate as well. Right, as it sits now, that's not going to be something we can integrate very easy. So we'll go ahead and have to find the PFD first. So the first thing we want to do is we're going to want to factor everything out, make sure there's nothing kind of in common. So for the numerator, I see that I have a trinomial. And I see that I have second power, first power constant. So we'll go ahead and try factoring this guy. So if we look at the first and last numbers, that's -6. And then we see the middle number is 7. That's actually not going to be factorable for us in any kind of nice way. So we'll go ahead and just kind of leave it the way it is. If we get something really goofy in the denominator, we can maybe revisit. In the denominator, we can just factor out an x. And we get x squared minus x minus 2. And we can factor that further. And so when we do that, again, we look at the first and last numbers there. We just got a -2. So we want two numbers that multiply to give us -2, add to give us -1. So that's -2 plus 1. And so we have our factored form now. And it looks like there's not going to be anything that'll cancel with the numerator. So we can go ahead and proceed with writing our partial fraction decomposition here. And you might be wondering to yourself, what's happening with that first factor? It doesn't look like x minus r. Well, this is going to be x minus 0. So no problem. We'll go ahead and continue here. We'll have a over x, or x minus 0, plus b over x minus 2, plus c over x plus 1. And so that's a constant over each of our linear factors. And the next thing we'll do then is we'll multiply both sides by the denominator of the left side so we can clear those denominators out. And when we do that, we should have a bunch of cancellation that happens. We'll go ahead and write that down here. So on the left side, all of the denominators will cancel. Sorry, all of the denominator will cancel. And we'll just end up with the numerator. On the right side, we again have to distribute this whole product. And when we do, for the first fraction, the x's will cancel. We get a times x minus 2 times x plus 1 plus b times x plus 1 plus c times x minus 2. So everything is left over except for what was originally in each denominator. That's the only thing that cancels. And so again, we're going to want to multiply everything out on the right side. And so you can see that this one is definitely going to be much longer than the last problem we worked with. So we have a times, we multiply these guys together, we get x squared minus x minus 2 plus b times x squared plus 1 plus c times x squared minus 2x. Sorry, there should be an x right here too. All right, we continue multiplying. Ax squared minus ax minus 2a, bx squared plus bx, and finally cx squared minus 2cx. And so again, we want to arrange all of our terms on our right side so that the powers of x are the same in each little group. So we got ax squared plus bx squared plus the cx squared there. That'll be one group. Next, we move on to just the x's. We got minus ax, and I'm actually going to write the positive one first. So plus bx minus ax minus 2cx. And then finally the constants. We just have the single one there, minus 2a. And then we'll factor. So factor out the x squareds from the first group here. We have a plus b plus c times x squared. Factor out the x's from the second group. B minus a minus 2c times x. And then minus 2a. And so again, this should be equal to the polynomial on the left side here for every value of x. And since that's true, it means that these coefficients must match up. So we have 3 equals a plus b plus c. 7 equals b minus a minus 2c. And finally, negative 2a equals negative 2. So it looks like the simplest one is probably this last one here. Divide both sides by negative 2. A should be 1. And we'll go ahead and substitute in a equals 1 into our other two equations. And so we get b plus c equals 2. And in the second one, we have b minus 2c equals 8. And so once again, we kind of have to solve this system of equations here. And let's go ahead and put these guys together in a system. We've got b minus 2c equals 8, b plus c equals 2. I'll go ahead and multiply the second one here by 2, and we'll do elimination again. So 3b equals 12, and that lands us with b equals 4. And we'll go ahead and put in b equals 4 here. 4 plus c equals 2, so c will be negative 2. And so that gives us the constants that we needed. And so we'll go ahead and plug those in. So we get that our original fraction here, x cubed minus x squared minus 2x, is equal to, we've got 1 over x plus 4 over x minus 2 minus 2 over x plus 1. And so now we want to integrate that. And this will be the same as integrating the original fraction we were looking at. And so for each of these, well, this first one is definitely just a natural log of x. Plus, when we look at this one, we've got integral of 4 over x minus 2. We can go ahead and bring that 4 out front. And when we do that, we get 4 integral 1 over x minus 2, which is actually just going to be 4 times the natural log of x minus 2. And all these guys do need absolute values. And then lastly, we get minus 2 natural log of the absolute value of x plus 1. So that's the nice thing about these linear factors, is that we will just end up with natural logs. Essentially, the numerator will end up as the coefficient of the natural log, and the denominator will end up in the argument of the natural log when we take this integral. Furthermore, we can actually combine all these natural logs together using log laws. And so we can take that 4 as the coefficient there, and in fact make it the power on the argument. Since it's a 4th power, x minus 2 will end up being positive, and so we can actually drop the absolute values. And the same thing happens here, except when we have the negative, it ends us up with the reciprocal, right? So we get x plus 1 under the fraction bar squared, because that negative 2 power. And so lastly, we can combine all these guys together, since there's addition outside the logarithms, it ends up as multiplication inside. And so our final answer would end up looking like a single natural logarithm with a bunch of factors and a quotient in its argument. So definitely a lot of work going on to figure out what these coefficients are at this point. There is going to be a slightly easier way to figure out what these constants should be equal to, and that's going to be called the Heaviside method. So as it says here, we're going to use the Heaviside method. Oliver Heaviside was the guy who originated this method. And what we're going to do is, since we know that the equation must be true for all values of x, instead of using that fact to equate the different coefficients, we're going to sort of go with a different route. We're going to instead say it must hold for any particular value of x. And so by choosing a value of x that eliminates some terms, we can easily solve for a, b, and c. Right? So what we'll do is we'll use this same equation here and kind of use the Heaviside method instead. So we want to pick some x values. So first, if x equals, and we want to think, what x can we plug in to eliminate maybe two of these guys but leave one of them? So let's say we want to eliminate both of these but leave this one. Well, if we plug in x equals 0, right, this little x term will become 0, and it will wipe this guy and this guy. And so that's going to be our strategy here. So if x equals 0, then, well, on the left side, we'll have 0 plus 0 minus 2. So we'll just end up with the negative 2. And on the right side, we'll end up with a times, well, 0 plus 1 is 1, 0 minus 2 is negative 2, and the other terms become 0. So we end up with negative 2a equals negative 2, so a equals 1. Next, if x equals, we want to pick a different x value that maybe gives us b. Right? So the only factor that's not involved in the b term is x plus 1. So how do we make x plus 1 equal to 0? We plug in negative 1. So we'll have on the left side 3 times 1 minus 7 minus 2. If we plug in that negative 1, we get 0 plus b times negative 1 times negative 3 plus 0. 3 minus 7 is negative 4, minus 2 is negative 6. And that's going to be equal to 3b. Divide both sides by 3. b is going to be equal to negative 2. And lastly, the only term that the c term is, or sorry, the only factor that the c term is missing is this x minus 2. So if we plug in x equals 2, it'll eliminate both of those. So we've got 3 times 4 on the left side, that's 12, plus 14 minus 2 equals 0 plus 0 plus c times 2 times 3. So 12 plus 14 minus 2, that's 12 plus 12 is 24, equals 6c. Divide both sides by 6, c is going to be 4. And so it gave us all of the same values that we had before, but yeah, as you can see, the work is in a much tighter place. There's a lot less steps involved. So we'll go ahead and default to the Heaviside method from here on, just so that we can keep our work much shorter than if we were comparing coefficients. Right, now we've got kind of a good feel for how not only to find these coefficients, but what the simple linear factors case will give us. It'll give us all these natural logs. And so we'll go ahead and expand now. If we start looking at repeated linear factors, what will that give us? So we're looking at a linear factor that has a power on it greater than 1. So we're going to suppose that we have this guy in the denominator. M is going to be greater than 1 and an integer. And so there must be a partial fraction for each power of x minus r up to and including that mth power. So if we have x squared times x minus 3 to the fourth in the denominator, we have to write then, first off, an a over x, then a b over x squared. So we have first power up to second power. For this second term, we have to have first power, second power, third power, and then finally the fourth power. So we have to start with the first power and go all the way up to the power that we actually see in the denominator. So the rest of it will remain the same. So what will likely happen in these types of problems is we'll actually have mixtures of some linear factors that are repeated and some that aren't. So we'll go ahead and modify our procedure to include these linear factors. So if we have the repeated one, we'll go ahead and include all of these terms for each of those factors from the first power up to the nth power. And as it says here, this gets weird when we have just an x to a power in our denominator. So why is that weird? Because this is actually a linear factor with a degree m. Even though it looks like a non-linear factor, it is a linear factor. So x to the m looks like a factor of degree n, factor of degree m, but is in fact a linear factor with multiplicity m. So it's really x minus 0 to the m. And the reason that we have to say that is because in a little bit we're going to start looking at quadratic factors instead of linear, and we really don't want to confuse something like maybe x squared as a quadratic factor. It is a linear factor, it's x minus 0, but repeated m times. So we'll go ahead and take a look at what this does to not only our setup for finding our coefficients, but also, for finding our constants, but also for how it affects our integrals. So again, we'll go ahead and start by factoring in our integrand there. And fairly certain just by looking at this guy, if we multiply 5 and 2, we get 10. Positive 10, there's not really going to be a good way to factor our numerator. So we'll go ahead and factor the denominator instead. Apply an x squared there, and we get x minus 2 left over. And so we can go ahead and go straight to our PFD. So we have a repeated linear factor there. We have a over x then plus b over x squared. And then we have our c over x minus 2. So we had a combination of a repeated and a simple linear factor. So we have to put in our constants for our repeated factors and then continue on sort of in the regular fashion with our non-repeated linear factors. The rest of this process should be just about the same in principle here. We'll go ahead and multiply both sides by x squared times x minus 2. And some nice cancellation happens. On the left side, the denominator is completely cleared. On the right side, we do have to be careful to only cancel out what needs to be. So when we go ahead and distribute here, for our a, one of the x's will cancel. The other one will stay around. And we'll keep the x minus 2 as well. For b, both of the x's cancel. We'll end up with just x minus 2. And for c, neither of the x's will cancel, but the x minus 2's will. And so from here, we'll go ahead and use our Heaviside method. And we want to think about what x can we plug in to get rid of all but one of these terms here. And looks like the 0 here is going to work out just fine for us because we have an x here and an x squared here. So I'll end up with 2 equals 0 plus b times negative 2 plus 0. All right, so we get 2 equals negative 2b, and so b will be equal to negative 1. Moving along here, we have x minus 2's in the first two terms there, so if x is equal to 2, that will make that term 0. So we'll have 4 times 5 is 20, and then minus 6 plus 2 equals 0 plus 0 plus 4c. And so adding these guys up, we get 16 equals 4c, so c equals 4. And so now if we're looking at how can we maybe get a by itself here, there's not going to be anything that we can plug in to get rid of b and c that wouldn't also get rid of a. On the plus side, though, we do already know what b and c are, so all we need to do is plug in some value for x that doesn't complicate things too much. So we'll go ahead and just pick any other value of x that'll just sort of keep things as simple as possible. And so if we plug in x equals 1, we get 5 minus 3 plus 2 on the left. And on the right, we'll get a times 1 times negative 1 plus, and we'll go ahead and just plug in b and c. So we have negative 1 times negative 1 plus 4 times 1. So on the left side, we get 4 equals negative a plus 1 plus 4. I'll go ahead and move this guy up here. So we have 4 equals negative a plus 5. So negative a equals negative 1. That gives us a equal to 1. So our integral will be equal to the integral of, we can go ahead and put in our partial fraction decomposition with the coefficients, with the constants, sorry. Plus, let's see, minus 1 over x squared. And then c is 4, so plus 4 over x minus 2 dx. So for the first term and the last term, those are going to follow the same pattern that we had with those natural logs because we have linear factors in the denominator. So this only works for those linear factors. So I'll go ahead and put in that second one as well. But the term in the middle here does not have a linear factor. Instead, we're going to have to take a different route. What's nice about this one is that this is just going to be a power rule. But we are going to need to be very careful with that. Sometimes we'll end up having to do a u substitution or something like that. This is x to the negative second power. We'll go ahead and start working with our logarithms too. So plus natural log of x minus 2 to the 4th power. And here we'll have minus negative x to the negative 1st. Right, we increase the power by 1, divide by the new power. So we have natural log of absolute value of x, these should be multiplied together. X minus 2 to the 4th plus 1 over x plus c. And so that should be our answer for our integral. So it will slightly change our Heaviside method. We will end up with, when we have these repeated linear factors, we will end up having to usually plug in some other value of x that doesn't give us a bunch of zeros on the right. We'll have to do that at the very end after we've kind of figured out what all of our other constants are. And it does change our integral as well. We can't just use a natural log. So we're going to have to be very careful when it comes to doing our integral. Remember, linear factors will end up as natural logs. We'll have the numerator as a coefficient, and we'll have the denominator as the argument. When we have something higher than a linear factor in the denominator, we'll have to do that kind of on a case-by-case basis. In this particular instance, it was a simple power rule, but in future cases, we might actually have to use some u substitution as well. So we'll go ahead and expand on that a little further even, and talk about what happens when we don't have a linear factor at all in our denominator, when it's an irreducible quadratic. which is a quadratic that cannot be factored. So when we have irreducible quadratic factors of the form ax squared plus bx plus c, we're going to have something like this here that isn't going to be necessarily factorable. So we're going to call that irreducible. And we actually might even have repetition on that as well. And so when that happens, recall that the reason that we said that we would end up with just A, B, and C in the numerator is because these guys are all supposed to be, in a sense, these proper fractions. Right? The idea is that since the factors are linear, the numerator should be a degree less than that, so degree 0. And when we get to a quadratic, however, that's going to be degree 2, which means that the numerator can actually be degree 1. And so that's going to change things up even further. So if we have an irreducible quadratic, then the partial fraction decomposition will look like this. We'll actually have a linear numerator. So we'll have an ax plus b. So we're going to have to keep that in mind as well, that the numerator only has to have a degree of 1 less of the denominator. We can still end up having a equal to 0 in this case when we solve things out, but we cannot simply get rid of a to start with. We have to kind of find that out for ourselves. So if we're going to look at this particular guy here, we do have to remember that if we're looking at the denominator in this case, this is going to be a reducible quadratic. We're able to factor it into x minus 8, x plus 4. And this x squared, remember, that is not a quadratic. That is actually going to be a linear factor that's just repeated. So we're looking at a over x plus b over x squared plus c over x minus 8 plus d over x plus 4. So it's going to be very important that we are able to spot the difference between an irreducible quadratic and a repeated linear. And so I think x squared is really the one that's probably going to trip us up the most. Just remember, if it's just x with a power on it sitting by itself as a factor, that's going to be linear. So we'll go ahead and look at an example here where we have a repeated linear factor here, but we have x squared plus 1. That's going to be a quadratic, and that, in fact, is going to be irreducible over the real numbers. So when we make our partial fraction decomposition, we will have to keep in mind that we have both this repeated linear and this irreducible quadratic. So when we do that, we'll go ahead and look at the linear first. First power, then another fraction for the second power. And so that's our repeated linear from the first power to what appears in the denominator here, which is the second. And then we have our irreducible quadratic. So we go ahead and put that underneath. And we'll actually have to have something of first degree in the numerator, which will be cx plus d. The rest of the procedure, again, is the same in principle. So we'll go ahead and multiply both sides by this denominator that appears on the left. So we've got x minus 1 squared times x squared plus 1. X minus 1 squared times x squared plus 1. So we have on the left side the denominator is completely cleared. On the right, again, we have to multiply it all out and make sure we only cancel what we can. So only one of the x minus 1s will cancel on that a there, although both will cancel on b. For the irreducible quadratic, we have to remember that we're multiplying this entire product by the entire numerator. We're going to have to use parentheses, and the x squared plus 1s will cancel. We'll end up with x minus 1 squared multiplied by that. And so this is a case where Heaviside method is going to be super helpful for us so that we don't have to multiply all this stuff out. However, when we're looking at how an irreducible quadratic affects our ability to find our constants, we notice that in particular, next to b, we have x squared plus 1. Since that's an irreducible quadratic, it cannot be factored over the real numbers. That also means that it doesn't have any real zeros, if you remember back in pre-calculus looking at polynomial functions. We have no real zeros for this polynomial, which means that we won't be able to plug in an x to cancel this out. And so we're really not going to bother trying to plug in to find b right now. We'll try anything else that we can. So looking at the rest of our factors here, the only other factor we have is x minus 1. And so we'll go ahead and plug in x equal to 1. And that'll be the only zero that we have really that we can use here. So we have -2 plus 4 equals 0, plus b times 1 plus 1 is 2, plus 0. So we have 2 equals 2b, so b equals 1. Looking at our next possibilities here, again, x squared plus 1, we can't plug anything to get rid of it. But looking over here, we do have c times x. So if we plug in x equals 0, we can at least eliminate c. So we have 4 equals a times -1 times 1 plus, we know already what b is. So we'll have 1 times 0 plus 1 plus d times 1. Right, that's -1 squared. And so we'll have 4 equals d minus a. And so there's still 2 unknowns here, so we can't really deal with that at the moment. So we're going to have to figure out something else as well. We're going to have to, in fact, just kind of plug in some different x's. Again, keeping things as simple as possible so that eventually we can get, hopefully, a system of equations we can deal with. So probably the next simplest x value we can use is -1, just to keep the magnitude small. So we'll have +2 plus 4. Then we have -1 minus 1, -2 times 2 plus 1 times -1 squared is +1 plus 1 is 2 plus we have -c plus d, -1 minus 1 squared is 4. So we get 6 equals -4a plus 2 minus 4c plus 4d. So we get 4 equals -4a minus 4c plus 4d. And so that kind of gave us 3 unknowns. So we still have more work to do here. We're going to definitely need to plug in another x value. So let's try x equals, we'll go positive again, keep our magnitude small. So we'll go with 2. So on the left side, 2 times -2 plus 4, we get 0. 2 minus 1 is 1. 2 squared is 4 plus 1 is 5a. Then we have b is 1, so 1 times, we already know that's 5 there. Plus we've got 2c plus d, and we have 2 minus 1 is 1 squared is 1. And so in this case, we'll end up with 5a plus 2c plus d equals -5. And so now we have some equations with some unknowns here, and we'll go ahead and figure out what we can do here. So back up here, we do have 4 equals d minus a. We can actually solve for maybe d here. So we have 4 equals d plus a. Looks like I did that a little wrong here. And we forgot the plus 1. So we actually have 3 equals d minus a. All right, and let's see what else we can do. Looking at this guy here, we have 4s everywhere. We can write 4, if we divide by 4, sorry, on both sides, we get 1 equals -a minus c plus d. Where have we seen d minus a before? D minus a should be equal to 3. So we were able to get then, let's see, negative 2 equals negative c, so c equals 2. All right, so we can go ahead and use c equals 2, and let's see, we can plug that in right here. So we have 5a plus 4 plus d equals negative 5. So 5a plus d equals negative 9. And now we have two equations that have both d and a in them. We have 3 equals d minus a, and negative 9 equals 5a plus d. I'll go ahead and swap the order there. If we multiply everything in the first equation by 5, we get 15 equals 5d minus 5a. Add these guys together. We get 6 equals 6d, so d equals 1. And so we're almost there. If we have d equals 1, we can go ahead and plug that in. Let's plug that in here. So you have 5a equals negative 10, so a is going to be negative 2. So now we finally have a, b, c, and d, and we'll go ahead and combine those all together in our partial fraction decomposition here. And so we get that our fraction is equal to negative 2 over x minus 1 plus 1 over x minus 1 squared plus 2x plus 1 over x squared plus 1. And so we can see here that this is essentially a problem in and of itself. And so we use the evaluation of the integral as a separate problem in this particular case. So now we have this partial fraction decomposition. We'll go ahead and look at the integral separately. So I'll box this guy because there was quite a bit of work behind it. And then I'll copy paste it as well. So if we want to integrate this entire fraction here, it's the same as integrating its partial fraction decomposition. For the first term, we know that that should be negative 2 natural log of the absolute value of x minus 1. And because we know that that's a linear factor. However, the repeated linear factor is different. We'll have to kind of carefully look at that separately. And in fact, the irreducible quadratic we'll have to look at separately as well. Right. For the irreducible quadratic, we might even want to go further and actually split that up into two different fractions and make each of those a separate integral. So we'll go ahead and change this into 2x over x squared plus 1 plus 1 over x squared plus 1. So we'll go ahead and look at each of these integrals separately here. Looking at this guy here, if we take a u substitution, looks like it's pretty straightforward. We can actually just do a power rule on this guy. So 1 over u squared du. And so that's u to the negative second. And so we'll just do power rule there. Oops, u got a little messed up, sorry. We'll also do a u substitution here, or a substitution, we can't use u again. We'll go ahead and start looking at v. So dv will be 2x dx. We have a 2x and a dx here. And so this will be 1 over v dv. And looking at this last one here, this is actually just straight out of the table of integrals. This is inverse tangent or arctangent. And we'll go ahead and add our plus c on here now so we don't forget later. So you have negative 2 natural log of absolute value of x minus 1 plus, well, it turns into minus u to the negative first, right? Dividing by the negative 1 gives us that minus there. Plus natural log of the absolute value of v plus inverse tangent of x plus c. And we'll go ahead and back substitute for u and for v. So u should be x minus 1. And then v is going to be x squared plus 1. And so the last thing we can do here is we can actually combine the two natural logs. This is going to be 1 over x minus 1 squared. And so we'll go ahead and combine those in a sec here. And so this will end up with natural log of x squared plus 1. That's always going to be positive. Just like the square always makes the denominator positive. And so this will be our result. You probably want to put the argument of this natural log in grouping symbols as well. The fraction acts as a grouping symbol, so it's not necessary, but it does make things more clear. And more clarity is always better. Right, so as we can see, if we have an irreducible quadratic, the problem does get quite a bit longer. And it's a good thing we have the Heaviside method to kind of mitigate that. And so the last thing we'll kind of look at here is what happens if we have an improper rational fraction here, or sorry, rational function. I should say function. And so if we have that, we have to reduce the rational function to proper using division. So we're going to have to do long division, right? We can't use synthetic unless our denominator is already a linear factor. So we'll go ahead and do long division here. So we'll have to remember how we do that. We have x squared minus 4x plus 4. Right, we have to remember what do we multiply by our leading term in the divisor to get the leading term in the dividend. The other way that you can kind of do that is just by taking the leading term in the dividend and dividing it by the leading term of the divisor. And so we'll just get 2x here. We take that 2x, we multiply it by the entire divisor here. 2x cubed minus 8x squared. Place that 8x. And then what we have to do now is we actually have to subtract. So we'll go ahead and swap the signs on all of these. So nothing there, and we get just x plus 1. And so our quotient and remainder here, we get 2x plus x plus 1 over our original divisor, x squared minus 4x plus 4. So we can rewrite this integral as 2x plus the fraction x plus 1 over x squared minus 4x plus 4. And now we want to be able to take this fraction and do partial fraction decomposition on it. Right, we're going to end up having a split integral here. And while that first integral is easy enough to manage, we need to do PFD on the second. So we'll take a look at this fraction. we have to factor. Looks like we have x minus 2 and then x minus 2 again. So we have x minus 2 squared in our factored denominator. And so we'll have to use repeated linear factors in our partial fraction decomposition. We have a over x minus 2 plus b over x minus 2 quantity squared. So we'll clear the denominators again. We multiply by x minus 2 squared. And so we get x plus 1 equals a times x minus 2 plus just b. So if x equals 2, that's probably going to be our easiest way to go. Then we got 3 equals 0 plus b, so b equals 3. And then really we can use any other x value. Right? We don't really have something that can make b equal to 0, but we know what b should be equal to. So we'll go ahead and use the simplest x value we can, which would be 0. So we have 1 equals a times negative 2 plus 3. So negative 2 equals negative 2a. So a is just 1. And so up here, we have 2x dx plus, we rewrite it in our partial fraction decomposition, 1 over x minus 2 plus 3 over x minus 2 quantity squared. So for the first one, that's simple enough. Right, we're just going to increase the power by 1 and divide by that power, so we just get x squared. The second, we have a linear factor, non-repeated, so it's going to be the numerator is the coefficient of our natural log, and the denominator is the argument. And then lastly, we need to just pay some close attention here to our repeated linear factor. We usually have to do u substitution here. In this case, things are going to end up pretty simply. This will also be a power rule. So we increase the power by 1, that's the negative first power, we divide. And so our final answer here is going to be x squared plus the natural log of x minus 2 minus 3 over x minus 2 plus c. Right, and that's going to round off then partial fraction decomposition. As always, if you have any questions on any of this, please send me an email, give me a call, join me in office hours. Let me know however you want, and we'll go ahead and hash it out. I hope you guys have a great rest of your week, and enjoy.